All right, in this example problem, we're told that a person is pushing a playground merry-go-round, and we've got an image here on the left-hand side. And we know that they exert a force of 250 newtons at the edge of the 50 kilogram merry-go-round, which has a radius of 1.50 meters. Then we're looking to calculate the angular acceleration produced by the person on the merry-go-round if nobody is on the merry-go-round. So in other words, just the merry-go-round and this person's pushing the merry-go-round at the edge. We're given the mass and the radius, and we're told there's negligible friction, and the merry-go-round can be thought of as a uniform disk for its shape. Okay, once again, I will begin solving this problem. I've already got a sketch here, but I'm going to draw like an aerial view just to be clear of how this force is acting on the merry-go-round. So this is the merry-go-round, then I'm told that a force of 250 newtons is applied at the edge, so at the edge of a 1.5 meter radius disk, essentially. So I see here that the person is producing a torque on the merry-go-round. They are applying a force some distance away from the center of rotation, and I'll get into that in a second, but that's my sketch for right now. So I'm going to go ahead and just say that my force here is 250 newtons. Not my torque yet, I have to calculate that. The mass of the merry-go-round is 50 kilograms. The radius is 1.50 meters. And let's see, am I given any other information? I don't think so. I think that's everything we have. And I've been told, so I'm going to identify my unknown here. I don't have any other way to get more given information at this moment in time. So I'll say that my unknown is alpha. I want to solve for the angular acceleration of the wheel. Now, I know I don't have enough information to use rotational kinematics. I don't know anything about the initial or final velocities or time or anything like that. So I'm going to have to use my rotational dynamics relationships instead to solve for alpha. I know here that the only way I can get alpha is if I have the moment of inertia and the net torque. So in my head, I'm already thinking, okay, I need to solve for the moment of inertia and the net torque. So I'll go ahead and write that down. Right, it doesn't matter which one you do first. In this case, they're not dependent on each other. I'll go ahead and solve for the moment of inertia first. I've been told that the merry-go-round is a uniform disk. And if you go back to your chart for the moment of inertia equations, I know that for a disk, so the moment of inertia of a disk is actually just 1/2 times the mass times the radius squared. This is actually the equation for a cylinder, but a disk is just a very thin cylinder, if you will. So they have the same expression. So if I know the mass of the merry-go-round and the radius of the merry-go-round, I can very simply solve for the moment of inertia of the merry-go-round by plugging those values in. So I'll go ahead and do that now. If I plug in the mass and radius, it would look like this, and that is equal to 56.25 kilogram times meter squared. So that is my moment of inertia here. All right, now that I have my moment of inertia, I just need to solve for the net torque exerted on the merry-go-round. Now, in this case, the net torque is just the torque produced by the person. There's only one torque in this case. There are no other torques that I have to consider. I know this because I've been told to neglect friction, and the only information I'm given about a force on the merry-go-round is the person pushing it. So once again, remember that the equation for torque itself, a single torque, is the lever arm R. I know it looks like radius, but it's the lever arm, right? Or the distance they apply the force from the center multiplied by the perpendicular component of that force. But I know that this 250 newtons is completely perpendicular to R, right? This R happens to be both the radius and the lever arm, which is just a coincidence in this problem. The person happens to be exerting that force at the outside edge of the merry-go-round, which is also just the radius away. So in this case, they're the same, but they won't always be. So the torque produced by the person is going to be equal to that R times F perpendicular. So it would be equal to 1.5 meters, so that's how far away, multiplied by 250 newtons. That would be equal to 375 newton times a meter. And in this case, it looks like they're pushing in the counterclockwise direction. So I'm going to say that is a positive torque. And again, this is also just the net torque. I only have one torque in this problem, so net torque is kind of redundant. It's just the single torque. There we go. Now that I have the net torque and the moment of inertia, I can use my relationship here net torque equals moment of inertia times angular acceleration. I'm going to rearrange for alpha. So if I do that, I would get that alpha is equal to, I'm going to divide by the moment of inertia, the net torque divided by the moment of inertia. And now I can just plug in my values once I've solved for them. That would be 375 Newton times meter over 56.25 kilogram times meter squared. And I know the units aren't exactly the most beautiful here, but the meter will cancel with the meters squared, and so I'll actually just get a meter on the bottom here. And so my answer is 6.7, and this is going to be, again, in radians per second squared. If you don't believe me, this, again, the units here work out to be a Newton multiplied by 1 over a kilogram times the meter, because that meter cancels with the meter squared. And remember, a Newton is just a kilogram times a meter per second squared, like mass times acceleration. So that's actually this multiplied by 1 over kilogram times meter. My kilograms go away, my masses go away. That's just 1 over second squared. But remember, radians just kind of sneak in here when we're going from linear to rotational motion. So that's radians per second squared, if you didn't believe me. So 6.7 radians per second squared, positive, right, is my angular acceleration of the merry-go-round because of the net torque or the single torque that the person is producing on the merry-go-round. All right, so in order to solve this problem, right, I identified that I needed alpha, my angular acceleration. I was given enough information to solve for the moment of inertia and the net torque, and I used those values to solve for my angular acceleration using Newton's second law in rotational form. All right, let's take a look at another example problem.